50-50 chance of that being the case.
Okay, so shall I start now?
Yeah, if you'd like to start now. You're running the show. I'm just keeping tabs
by
on
the way,
stuff.
could you let me share the screen?
Oh, can I? Yep.
There are two instances
You should
of
hopefully be
me.
able to share. Sorry, this is the first time I've run it through Anesh's account. Are you able to share your screen now?
Yes, yes.
Good, great. Well, feel free to start at your leisure.
Okay, so I would like to thank the organizers for inviting me here. I'm Pavlo Gavrylenko, and I'm going to talk about our joint paper with Andrei Mashikov and Artyom Stoyan. This one. Okay, so the plan of my short talk is the following. So first, I will make some introduction. This will repeat a part of advocacy talk, but it will contain some extra details related to expansions around infinity. Then I will tell the story about arbitrary central charge, about how can one quantize Pavlov equation in order to get arbitrary conformal blocks. And then another part of the story will be a little bit independent from this. This will be about C equals infinity limit of conformal blocks. And after this, we can discuss anything. Okay, so let me start with the introduction. So our main object will be the Pavlov equation. This equation, which has no free parameters, it's the most degenerate equation in one of the directions in this degeneracy diagram, which you could remember from Albert's talk. So this equation can be obtained from compatibility of the following 2 times 2 linear system with matrix AFZ containing 2 regular singularities at 0 and at infinity, because you see here it's 1 over z squared, and here it's 1 around infinity. And the second matrix in this pair is this simple one. Okay, so we will need just to remember that there is such a linear system. We will choose it for the computations. So as usual, this equation is Hamiltonian. It has this canonical momentum. Hamiltonian written in terms of velocity, and maybe it's nice to know that if we perform the following change of variable, then this equation transforms into a radial Sandgren equation. So it's actually very simple. At least it looks simple. So what we know about a solution of this equation? We know that its general solution can be given by some explicit formula, which is a convergent series around t equals to 0. This is this was first found in this second paper by Huminer and Lisoway. And then the first proof of this formula probably was in Mishas and Anton paper, this one. So the formula is as follows. This Pannoia transcendent equals up to some factor to the ratio of two so-called tau functions squared. These tau functions are given by Fourier series of C equals 1 regular conformal blocks B with some prefactors depending on the bounce functions. And as it should be for any general solution of second order equation, it has two integration constants, eta and sigma. And these integration constants are related to monodromy data of initial 2 times 2 linear system of this one. Monodromy data looks as follows. We have two solutions at 0, two solutions and at infinity. Since those are regular singularities, we have one dominant solution, another one subdominant, and this matrix is mapping dominant to subdominant and vice versa. I have this form. Those are M0 and M infinity, and there is also a third matrix which maps 0 to infinity, and so this matrix contains another monodromy datum eta. So, okay. So now just to define everything, I will say who are these conformal blocks. This C equals 1 conformal blocks in particular. So in any questions? Okay, so since we're talking about versor algebra, let us define it. So this is versor algebra, infinite dimensional algebra with the following commutation relation. And its irregular conformal block is given by the matrix element of basically t to the power L0 between two so-called Whittaker vectors, W. These Whittaker vectors are such vectors which are killed by all generators greater than 1, and it should be eigenvector of L1. And in our case, this vector should be found as some vector in the completion of the highest weight module of the Sarasara algebra. So it has some expression of this kind, and so it can be generated from the highest weight vector. This one. And there is also this convenient parameterization of the central charge in terms of letter B, and of eigenvalue of L0. And we have two particular limits which are usually interesting. First one is b equals to I, it's c equals to 1, and this gives those conformal blocks which appear in the expansion of the tau function. And there is also a b to 0 limit, which is c equals infinity. In this case, there is a statement which I'm not sure how to say it precisely. Probably it's a conjecture if we want some very gross proof, but there is more or less no doubt that such formula should hold always. So in b equals to 0 limit, this conformal block exponentiates, and what stays inside exponent is called quasi-classical or Nekrasov-Shakashvili conformal block. Okay, so this was about conformal blocks in the region around t equals to 0, where such conformal blocks exist. So, but and also some remark which will be useful later, that we can rewrite the Spinelli's equation in terms of tau functions only, and this will be equivalent to initial formulation. So this Spinelli's equation can be written as a system of these two bilinear relations on tau functions, which are written in terms of Hirota derivatives. In this case, those are usual Hirota derivatives. And why it is useful? This is because we can write these bilinear relations and as relations on conformal blocks, and Misha and Anton proved this bilinear relations on tau functions starting from bilinear relations on conformal blocks, and they are called block relations. And it turns out that actually there are such relations between conformal blocks, not only for c equals to 1, but for arbitrary c. Misha and Anton have them. Okay, so now what about the main part of my short talk? So it is known that this Penrose equation has a quite similar expansion around infinity. It was found in this paper by Itz, Leslie, and Tichy. There is a very similar formula, which is written in a bit in a little bit different variable, which is 80 to the power 1/4. So this formula has the same structure of the Fourier expansion. So there are two monotony data, rho and nu, which are related to sigma and eta by such formulas. And there is this Fourier transformation in nu. And this formula contains some function which is labeled here by b infinity. This function has no CFT definition yet, but we can compute its first several orders. There is the following series up to the r to the -5. This is an asymptotic series. Of course, and it's quite similar to what happens in the bottom row of Pavlo generation diagram, which is all in Alba's talk. And it is very interesting what is the meaning of this function and what are its generalizations. So the question is how to see some analog of this conformal block at infinity for some other values of the central charge. And what is the idea? So the general statement is the following: if we want some other central charges, then we have to consider quantum equation instead of a classical one. I will say a bit later what it means. So quantization, it's not a p-deformation. It's a different procedure which can be actually done together with the p-deformation. And actually, it's not the only way to get arbitrary central charge. There are some other ways to do this, which work for some special values of the central charge. For c equals infinity, for c equals to -2, and probably for some other central charges, which can be used to cross-check what we get from this quantum Pavlov equation. So there are some motivations for this quantization. So probably the main motivation was that bilinear equations existed for arbitrary central charge, but they were not used to construct any tau functions except for c equals to 1. The hint that there should be some quantization was contained in the Irregular paper, where the construction gave a quantum monodromy data for other central charges. And another hint was from cluster algebras, because if we work with skew-deformed equations which have cluster description. Questions? So if you work with cluster algebra, then quantization is very natural and straightforward. So in combining these motivations, we obtained with Mishabert and Remarshkov a solution of a quantum cube in over 3, which was actually in terms of predefined conformal blocks with an arbitrary central charge. So now we do the same for this differential equation, not for difference one. So first, what is quantum penalty 3? So in our approach, this is some quantum Hamiltonian or Heisenberg evolution of the operators, which is given by this formula, which reminds us this radial Sand-Gordon equation, and it also needs a canonical commutation relation, which is written in terms of this deformation from C equals to 1 parameter. It's so it's some homogeneous parameterization where B squared is the ratio of epsilons. If B squared equals to -1, then this vanishes, and we go back to non-quantized equation. In this case, we have the same formula of a solution, which is written in terms of a ratio of two quantum tau functions. And what this quantization means at the level of the tau functions, it means that we have here a quantized monotony data. There is a rho hat and nu hat, which now have this bracket. And there is also some shift operator which shifts central charge, but we will actually we will not need it actually. So now it was only the answers which should solve this equation, but we can substitute it and find some explicit formulas. So first we find what is the deformation of the prefactors in Alba, do you have a question?
Yes. Can I ask you a question? Like, so if I think of the standard Pavlov equation, like they appear in physics in many ways, like in 2D gravity or like the 3 is like the 2D Ising model. Does this quantum deformation, does this quantum Pavlov also has some realization in more physical context, like if I think in the term like Pavlov 3 and the 2D Ising model? Do you have any application for this quantum Pavlov?
I don't know. I think that it's a Schrödinger formulation, not a Heisenberg one, should be a kind of non-autonomous Schrödinger equation. So I think it has some application, but only in this Schrödinger picture.
Okay, thanks.
Sorry, can I ask a question as well?
Yes.
So epsilon and epsilon 1 and epsilon 2, they're operators as well?
Yes.
Yes. Okay. Yeah.
But the only operator which which doesn't commute with them is this shift operator A.
A. Okay. Yeah. Yeah. Okay.
And actually, naively, it doesn't enter this formula. We will need it if we want to prove some bilinear relations on the tau functions. So here it cancels. So W hat is some function of only two non-commuting variables, rho and nu.
Okay. Thank you. Thanks.
And is there some general reason why we should expect that type of commutation relation, or for epsilon1 and epsilon2 with the shift, or
do you mean this one?
yeah.
More or less it's because bilinear relations in emissions and endurance paper contain conformal blocks with different central charges.
Yeah, so basically
So,
one finds them empirically by knowing already the bilinear relation from CFT.
Yes, and also there are motivations coming from the cluster algebras.
Okay.
There should be correct permutation relations between a big set of tau functions.
Mm-hmm. Thank you.
Yeah. So, so now there is this answer for the kind of as a 3-point prefactor, maybe better to say for the structure constant. So it's just deformation of that C equals 1 formula. And we can also compute some terms of expansion of this conformal block at infinity. So there are some polynomials in nu and in 2 epsilons. For the 3K, there are some explicit examples. It gives a kind of analog of conformal block at infinity, which is defined for arbitrary central charge, but it is an asymptotic series, and I would like to know, for example, if there is any definition which is not asymptotic series, but some true function. Okay. So now we have such formulas, and I will also I can also say a few words what was done technically to get these formulas. So if I remember this bilinear relations for the tau functions, then I can say that basically we substitute this answers for the quantum tau functions in quantum bilinear relations, and find some bilinear relations for conformal blocks at infinity only. And then we solve these equations, which gives us such expansions of conformal blocks. Okay, so what are other answers? So if we want to recover its Lissouin-Tichy results, we have to substitute epsilon1 equals to 1, epsilon2 equals to -1. So recover this known formula. So another limit is c goes to infinity. This defines some function which is also asymptotic series in R. So we can also take it's this way Tichy formula, rotate it a little bit to the imaginary axis, and then compare to Tracy and Wu solution, and making such an identification, we find some explicit integral representation for these conformal blocks at high times integer points, which is not asymptotic series, but the actual function. And it turns out also that we have formulas of the same kind for c equals to -1, and to get this, we need to take a Grassi-Katsuda and Main paper about a BGM to this Bernstein and Chechkin paper about c equals to -2, and then find something like this. There are actually infinite a series of such formulas as well. Okay, so some time is over. So I will just say a few words about c equals to infinity. So as I said already, there are several different ways to get arbitrary central charge, and some of them are not quantum. In this case, they're just a little bit independent. So such a definition of c equals to infinity conformal block is the following. We just take the tau function which is in the denominator, find its zero in the variable rho, we call it rho star, and write it in terms of some function. This function, we can call this function c equals to infinity conformal block. It's actually not a definition because it defines only a new variable of this function. To get the full definition, we need to say that this function is the value of a regularized action function. It should be the action on the trajectory going from 0 of the tau function to infinity. Basically, it's just integral of Lagrangian regularized in some nice way. And why this definition is nice? Because we can, because if we have an integrate of Lagrangian, we can differentiate it with respect to nu, with respect to t, and we can also compute it explicitly in terms of the tau function and in terms of some monitoring data. And this formal work. Yes. So computing these derivatives, we get such formulas which can be familiar for some people. And probably this approach is equivalent to what Leclerc does using Bertollet-Lagrange derivative formulas for the tau functions. And also going in this direction, we can find the link to CFT correlators, because as it was done in between Olkianounikas with the Molotov paper. So finally, performing this procedures, we get such expansion of conformal block in infinity, which coincides with what we computed from that general formula for the quantization, from the quantization. Okay, so there was this definition. Remember, this conformal block is related to the movable pole, to definition of the tau function, and this gives the link to spectral problems of 2 times 2 for second order Schrödinger equations. So if you remember Albert's talk, then to get a Schrödinger equation from 2 times 2 linear system, we need to put some tau function equals to 0 to ask that that finally we get a normalizable solution, and also in this case we have one more step. We need actually to get some other tau function, but it's too much details. So the spectral problems which I have here are this cosine potential and hyperbolic cosine potential. And the answer for their spectrums in terms of this conformal block are the following. So energy of the nth level is just given by the logarithm by the derivative of this conformal block at infinity in variable r. So a number of the level enters just as an argument of this conformal block. Here it is. It's different from the vicinity of t equals to 0, where we had to solve some non-trivial equation to get something. In this case, we have just explicit formula depending on the energy level. So, and there is some expansion which is harmonic oscillator plus some corrections. Okay, so that's all. And now open question for possible discussion. So the main question for me is what is this conformal block at infinity? Are there any formulas for its coefficients and so on? Another question is the following. So we saw that in general, this can be found as some asymptotic series, but asymptotic series, it does not define a function uniquely. But nevertheless, if it solves if such expansion solves Pauli equation, that we know that this conformal blocks should be some actual functions. And we know two examples where there is alternative definition of these functions. Those are for this case with the integral representation. Another example is the spectrum of hyperbolic cosine potential, where we have actual energy levels, and we have some actual formulas for their energies. So, and there are also some other questions which are listed here. So, I'm sorry for an out of time. And do you have any questions?
I have one question. Well, I have many questions, but I'm trying to understand exactly what is the relation between this arbitrary conformal charge and the quantization. In other words, is there some sort of a direct map? What I'm trying to understand is that, is the following statement true? If I take normal Penleve equations, you're looking at some conformal blocks at c equals 1. And then if you're looking at the quantized version, you're going to c equals infinity.
No. If you look at quantized version, I mean quantized in this sense, in a sense that it is a Heisenberg evolution equation on some quantum function W. Then it gives arbitrary central charge.
So where is this arbitrariness coming from? So what I'm trying to understand is that what is the value of central charge dependent on?
It's this kind of constant epsilon 1 plus epsilon 2, and central charge is so remember c equals to c equals to 1 plus 6 epsilon 1 plus epsilon 2 squared over epsilon 1 epsilon 2.
So where in, okay, maybe a very stupid question. Where is Penleve 3.3 in this picture? So in other words, what exactly are you doing to get to this slide? So I'm trying to understand what you mean by quantization and how you're doing it.
So it's
But okay, so I think my main question is it the fact that you're quantizing the Penleve equation itself, or is it the Lax matrices that are operator valued?
probably on both is true. Here is quantized Penleve equation. It's equation for operators, for W and for W prime.
So where do the epsilon1 and epsilon2 come from?
What do you mean by come from? Where are they in this equation, or where it should be solved?
No. I'm asking, so if I just take Penleve 3,3, I don't have any epsilon1, epsilon2, right?
Yes.
So are you artificially putting it in these equations? I mean, what is the origin of these parameters in your quantum Penleve?
So the main origin is here. We have operators of coordinate and momentum which do not commute, and their non-commutation depends on epsilon1 plus epsilon2. It's a parameter describing difference from c equals to 1. So epsilon1 plus epsilon2 is quantumness parameter of this problem.
Like Planck's constant. So if when epsilon1 plus epsilon2 goes to 0, then you retrieve the classical Penleve equation, I guess.
Yeah,
Yes.
so then my question is, because epsilon1 and epsilon2 seem to be playing separate roles, not a combined role. In other words, in the other equation, in the equation on your right, you only have epsilon2. So what I'm trying to understand is that just from a mathematical point of view, if I don't know anything about the central charge, if I don't know anything about, I mean, just starting from Penleve 3,3, how do you then go from just one Planck's constant, for example, to epsilon1 plus epsilon2? I don't know.
Yes, but you see, if in quantum mechanics, so there was this formula for central charge, or maybe I won't read it. So in quantum mechanics, we also have this formula: x hat 2 dots equals minus u prime of x. But it's not enough to define our system. We need to say that a commutator of P with, or not P, commutator of x dot with x equals to a minus I h bar over m, probably. So the first equation is absolutely the same as in classical mechanics, but it's not enough to define a Hamiltonian evolution. Probably it's one of those examples where it's better to work with a equideformed equation rather than with a differential one. And because there it's just obvious. We have some algebra automorphism, and to make it well defined, we need to say that W of t is one variable, W of qt is another variable, and since the equation's second order, it maps W of t and W of qt to W of q squared t and W of qt, and we need to define the algebra structure for these two variables. Only if you do this, it makes sense. I don't know. Was it?
I think
At
the
least
point
in
is that
projection.
normally you just have one parameter like h bar, and it looks like there's two parameters here. So that's maybe that's what's.
Yeah.
But actually, all this depends only on the ratio of epsilon1 and epsilon2.
Mm-hmm.
So,
okay.
This so we see here that it should be some rescaling of parameter t by epsilon by raising to the power of epsilon2. Something like this, probably.
And if you have this quantum Penrose equation, and we consider another quantum Penrose equation where you exchange epsilon1 and epsilon2. So are the solutions of these two different quantum Penrose equations related to each other in some way?
I don't know actually, because no, I don't know. At least conformal blocks here are not symmetric. We have something like this.
Maybe just to add something, this two Planck's constant aspect. Like if you just think of it from an integrable system point of view, forgetting about partition functions or conformal blocks, whatever. You just start from the an autonomous integrable system, then you have two parameters because you're doing the autonomization, and you have a parameter that governs that, and that is epsilon2, and that's why epsilon2 is rescaling t. And then you have the Planck's constant that governs the quantization, which is another deformation parameter. And so this is why you have two, because if you start from the classical isospectral integrable system, then you have these two deformations and you're doing both.
Yes, thank you. It's true, of course.
Can I ask something? So before you mentioned that this quantum Penrose, if you think maybe from a more physical point of view, you may relate them to Schrödinger equation with time dependence. But is this just an expectation, or is it something that you concretely know is gonna be like that? And is it the time going to be like epsilon1 plus epsilon2 in the Schrödinger system?
No, so I have not checked that this autonomous Schrödinger equation works, but it should work in principle, because we have BPZ equations which are exactly non-autonomous Schrödinger for Penrose 3. So probably the mapping should be of this kind, that position of degenerate field is eigenvalue of W, and time is time. And
yeah, I understand. This you are mean this is going to be the BTC equation before taking the NS limit.
Yes, it should be like this. And probably the statement that this BPZ equation is satisfied will be some kind of an academic equation, but
Yeah, thanks. Can I ask you on another question? So before when you have, I think, C equal 2, you have this you can write this conformal block like B infinity.
C equals minus
Those
2.
are not conformal blocks. I don't remember, but if you go back
To this formula. So
yes, here you have this integral. With C equal minus 2, you have this integral. Do you have an analogous of this when C is not minus 2?
no.
But can
No, the closest analog is for C equals to 1. I mean, this integral.
yeah, but for yes, but like if I want to have the 2 epsilon 1 and epsilon 2 switch on, can you get something similar or no? Like even
I have no idea. Probably I have to ask you about such examples.
Yeah, exactly. I don't know any example, but I would like to know. That's why I was asking. Yeah, thanks.
So this C equals to minus 1 came basically from your factorization of the tail function into two spectral determinants, and this is a plus and a minus from your paper.
Yeah, but yeah, I was just even like I don't not maybe the full matrix model, but this this nice expression with like the integral of the z e to the minus r, the one that you have downstairs. If maybe you had something like this for the 2 epsilons.
I don't know. I tried to get some formulas, but without any success.
Okay, thank you.
You have a question?
Yeah. I actually have a question about the monodromy coordinates that you use in these expansions. So if you go back, I think it was slide 7 or 8, and you have
and this?
Yeah. So if I consider, the usual C equals 1 expansion, I have, let's say, sigma and eta, and these are trace coordinates, and I can think of them as Fenkel-Nielsen coordinates for that Pans decomposition. So
yes.
And then here I have this rho and nu, and if I remember from your paper, these are more Falcon-Cherov type coordinates.
Yes. Probably it's from a common communication paper.
Yeah. Yes, but in common Longian-Teschner, I think this identification. But if I think they have this, but when they expand, they make the distinction when they expand at t equals 0 or at t equals infinity. And at t equals 0, they have Fenkel-Nielsen-like, and at t equals infinity, they have Falcon-Cherov. But maybe I'm...
Yes.
Yeah. So here I have like 4 possibilities. I have C equals 1 at 0 or infinity, and then I have C equals infinity at 0 or infinity.
No, sorry, probably I missed. So in their paper, they had only C equals 1, right?
Yes,
yes.
Yes. But and so this is not really what's happening in their paper, because here you're doing no. So this is C equals 1 conformal blocks at infinity. But then you can also have, in this discussion that we had, you can also have C equals infinity at t equals to 0 or at t equals infinity.
Yes.
And is it still true that if I expand at 0, I have some Fenkel-Nielsen-like, and at t equals infinity, also for the semi-classical conformal block?
Yes, this semi-classical conformal blocks depend only on one of these variables. they depend on, one depends on the sigma, another one depends on nu.
I see. So the C equals infinity. So C equals 1 depends on both, while C equals infinity depends only on one of the two.
C equals 1 tau function depends on both
Right.
sigma and rho. Yes, conformal blocks are the same, of course. Sorry, one depends on sigma, another one depends on nu.
But I think you also have a parallel story for C equal infinity. This is the question, C equal infinity is like quantum periods. And then if you are in the weak coupling region, like the T around 0 in this case, you have Fenkel-Nielsen. But in general, you have Fogg-Goncharov, right? And you also have this type of transformation also for the C equal infinity.
Let's see. And
but I'm not sure for example, I remember that one of the transformation is actually something like the one instead something like sin over sinh, but it's more like cosh over sinh, but maybe that's just that.
Yeah.
But they really have a similar structure also for C equal infinity.
Yeah. Maybe, yeah. Let's see. But can I understand it like conceptually? Like, why is this the case? Like, if I wanted to extrapolate it to P6 or Schlesinger system, like, why, if I expand, like in that case, I can expand, let's say in the sphere with 4 punctures, I can expand at 0, 1, or infinity. And like, how would I think that if I expand at 0, I know that I have still some Fenkel-Nielsen like coordinates from the Pence decomposition, but at 1 or infinity, what should I expect to happen?
Absolutely the same, because if you switch to different regions, you have actually just different Pence decompositions. So everything will be of Fenkel-Nielsen type. And I don't know, for example, where to find Fogg-Goncharov. In that case, probably it should correspond to some limits when dimensions go to infinity, and we take expansion around some different points, but probably it's just wrong.
I see.
It's basically what I asked Alba. So for C equals to 1, we have these transformations between different regions around 1, around 0, and around infinity, and they correspond to some trivial dualities in the gauge theory. And here we also have something like this, the duality between a theory where monopole is massless and the weak coupling region. And the question is, what is the general picture? So what are these dualities?
Thank you.
But by the way, does anyone have any ideas? I don't know. At least, is it a correct question about kind of non-perturbative definition of such conformal blocks? So can it be, for example, so that some function has some asymptotic series, but it does not correspond to any nice expression which can solve Pavlo equation if you substitute it into this formula. So I'm asking because, for example, if you look at this formula, it is well defined only for R on the real line, because we have summation over all integer numbers, and
but you can regard this as a definition of B, non-perturbative definition of B.
So but do we need to prove anything, or we know from we know for some reason that the tau function has this formula?
The tau function is periodic with respect to nu.
So yes, I see. So it says that we can just take tau function, which is function, and then take its Fourier transformation.
Yes.
Right.
Mm-hmm.
And so it defines all this product of B infinity times exponential times e to the times r to the power 1/4. And once we define something like this, is it true that we have no guarantee that it will have this expansion valid for arbitrary r, not only on the real axis?
Well, you can normally extend a Fourier series. You can analytically continue a bit off the real axis, but I don't know what you can say globally. But
but Pasha is asking about the dependence on R. So so the question is whether so we can define B infinity as the Fourier coefficient of the tau function expanding with respect to monodromy. Mm-hmm. And we can most probably prove that this B infinity defined in such a way will have a given asymptotic expansion on the real axis of R now as a function of R. And the question of Pasha, as far as I understand, is so can we prove anything about the asymptotic expansion of this B infinity, but for arbitrary argument of R?
Yes.
That
so basically, I'm looking at this formula as this integral representation. So it works perfectly for a purely imaginary R. It's even better convergent than for real R. But it works only for integer values of I knew where this series for the tau function actually terminates in one direction. And this is why it is well defined. So conformal blocks at I times integer points are very good objects, but the tau function breaks down. So I don't understand what happens if we go out from this point IN. Does anything special happen or not? Probably it's just some stupid question.
So R is dependent on what precisely?
So R,
yeah,
is t to the power 1/4.
So essentially, you want is it valid to translate your problem into how you study the asymptotics of say the solution of Penleve at different limits of t?
I don't know. So,
but actually, sorry, I can wait. Sorry.
Oh, that was it. I was just trying to understand what the relation.
No, because for example, in what you show before, where you have this matrix model, you take nu to be an imaginary, right?
yes.
So there, the Barn function are going to be killed if you take n negative, right?
Yes.
And for example, so if you take nu to be I times an integer, then of course this makes sense for any r, right? Because the sum it's only r. I mean, not for any r, but since the sum.
Yes, it works probably for positive. For r's with positive imaginary part. So the series is convergent.
Yes.
Probably it's so. And probably another question of the same kind is the following. So we know this solution to the spectral problem of the hyperbolic cosine potential, and we know that so for cosine potential we have something strange. We have we need to find positions of the exponentially narrow bands as a function of the number, and this is not well defined because it's defined only up to the width of this band. And for a hyperbolic cosine, we have actual energy. So it seems that this function for cosine potential is not well defined, but for hyperbolic cosine, we have some actual function, but which is defined only for integer values of n. And yeah, I don't understand, for example, what is the continuation of this function for arbitrary n? Is there any definition of it?
Can I just ask a naive question? When you quantize this problem, you got a Schrodinger equation, a non-autonomous with a time-dependent potential, right? Is that right?
What?
When you quantize the Penleve 3, you got a Schrodinger equation with a time-dependent potential. Is that right?
Yes, I think we will get this. I would say I'm almost sure, but we haven't done it yet.
And so when you're asking about energy levels, what does it mean? Because to have energy levels, if the potential is time dependent, I mean,
no.
States or
no, I'm asking about this c equals to infinity case.
Okay, there you really have a time independent potential in the end. Is that? You really have energy levels then, yeah. Okay.
Yes. So it's interesting.
Yeah, I just wanted to understand that because yeah. Okay.
Do you have other questions?
Thank you.
No, the hand was just left. Do I have to manually? You have to manually lower it. Okay.
So it sounds like we've reached kind of a natural finishing point. Does anyone else have any questions before I end the recording? Okay, well, thanks very much, Pasha. That was really great, and I really enjoyed you leading that. I'm sure I'll see some of you again at the afternoon talk, so thank you all very much for attending, and let's all thank Pasha again.
Thanks, Pasha.
I'll hang around while you all leave.
Thanks.
Thanks everybody for attention.
Okay. I'll see you later then.
Yeah. See you today, maybe.
Yeah.
Just to ask, this is all in your paper with the latest paper, right?
In the paper with Trimmer School and Artemsteyan.
Okay.
And if you ask me if it's horribly big, then the answer is yes.
Well, I just need a reference because, okay, well, I'll talk to you later. Once I understand things, maybe I'll have more questions.